In this lecture, I'm going to be talking about another article in contrastive learning, but we focus on good views and what makes for good views for contrastive learning. Contrastive learning between multiple views of the data has recently achieved state-of-the-art performance in the field of self-supervised representation learning. Despite its success, the influences of different view choices has been less studied. This paper used theoretical and empirical analysis to better understand the importance of view selection, and argued that we should reduce the mutual information between views while keeping task-relevant information intact. To verify this hypothesis, we devised unsupervised and semi-supervised frameworks that learn effective views by aiming to reduce their mutual information. We also consider data augmentation as a way to reduce mutual information and show that increasing data augmentation indeed leads to decreasing mutual information and improves downstream classification accuracy. As a byproduct, we achieve as new state-of-the-art accuracy and unsupervised pre-training for ImageNet classification. Just a quick review of mutual information, that the mutual information of two jointly discrete random variables, x and y, is just this double sum. And in terms of PDF work, because of its continuous distribution, we just replace sum with the integral. But views are commonly different sensory signals like photos and sounds, or different image channels or slices in time, but may also be different augmented versions of the same data tensor. If the shared information is small, then the learned representation can discard more information about the input and achieve a greater degree of invariance against noisy variables. How can we find the right balance of views that share just the information we need, no more and no less? So we investigate this question in two ways. We demonstrate that the optimal choice of view depends critically on the downstream task. If you know the task, it is often possible to design effective views. We empirically demonstrate that for many common ways of generating views, there is a sweet spot in terms of downstream performance where the mutual information between views is neither too high nor too low. And our analysis suggests that info-min principle, a good set of views are those that share the minimal information necessary to perform well at the downstream task. This idea is related to the idea of minimal sufficient statistics and the information bottleneck theory, which has been previously articulated in the representation learning literature. This principle also complements the already popular InfoMax principle, which states that the goal in representation learning is to capture as much information as possible about the stimulus. And then they argue that maximizing information is only useful insofar as that information is task relevant. But what are the optimal views for contrastive learning? Given two random variables v sub 1 and v sub 2, the goal is to learn a parametric function to discriminate between samples from the empirical joint distribution and samples from the product of marginals. The resulting function is an estimator of mutual information between v sub 1 and v sub 2, and the info and CE loss has shown to maximize a lower bound on the mutual information between v1 and v2. In practice, given an anchor point v1, the info and CE loss is optimized to score positive when we draw v sub 2i from the probability of given v1 the probability of V2. So this higher compared to a set of K distractors. Those are negative samples, and minimizing this loss equivalently maximizes the lower bound. And this is the sweet spot, because this is the schematic of multi-view contrastive representation, where an image like this image is split into two views and passed through two encoders to learn an embedding where the views are close relative to views from other images. When we have views that maximize mutual information between V1 and Y and V2 and Y, and minimizing the mutual information between V1 and V2, these are three regimes. The missing information, which leads to degraded performance due to the fact that it could be less than the mutual information. The excess noise, which worsens generalization due to additional noise. And sweet spot where the only information shared between V1 and V2 is task relevant, and such information is complete. To understand how the choice of views impact the representation learned by contrastive learning, we construct a toy dataset that mixes three tasks. We build our toy dataset by combining moving MNIST, and which consists of videos where digits move inside a black canvas with constant speed and bounce of image boundaries, with a fixed background image sampled from STL10. And so we call this new dataset the colorful moving MNIST. And we fix view V1 as the sequence of passed frames x1 through k, and we consider V2 as a single image and constructed by referring to higher frames. And one example of visualization is in figure 10, and this is the illustration of colorful moving MNIST. And the first view V1 is just a sequence of frames containing the moving digit. The match second view V2 plus shares some factor with xt that V1 can predict, while this is the unmatched V2 minus does not share a factor with xt. And you see how mutual information shared by the views would affect the representation quality. We designed unsupervised and semi-supervised methods that synthesize novel views following the info-min principle. We extend the color space experiment by learning flow-based models and that transfer natural color spaces into novel color spaces from which we split the channels to get views. Practically, the flow-based model G is restricted to pixel-wise convolutions and ReLU activation operating independently on each pixel. We try both volume preserving and non-volume preserving. For an input image X, the splitting over channels is represented as X1 and X2 through 3. X hat signifies the transformed image. And the idea is to leverage an adversarial training strategy. So given X hat, we train two encoders, F1 and F2, to maximize this mutual information between X1 and X2 through 3. But meanwhile, G is adversarially trained to minimize the mutual information between them. So we are minimizing and maximizing optimization, so it's min-max. But alternatively, one may use other mutual information bounds, but we found the mutual information in INCE works well and keep using it. And we note that the invertibility of G prevented from learning degenerative or trivial solutions. We assume a handful of labels for the downstream task are available, thus we can guide the generator to retain the mutual information, and we introduce two classifiers on each of the learned views to perform classification during the view learning process. So we are minimizing the maximization of one of our objectives is just the unsupervised, which will reduce the mutual information, but the other one is supervised and we keep this mutual information. And C1 and C2 here are just classifiers. The INCE term applies to all data, while the latter two are only for labeled data. In each iteration, we sample an unlabeled batch and a labeled batch. After this process is done, we use frozen G to generate views for unsupervised contrastive representation learning.